Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, hi, it's good to have Ola Svensson with us. It's been a while since he came here. We've been trying to get him for a long time. And he's going to talk about a very new result. I believe this is the first time he's giving a talk on this, on kMedian. So yeah. Ola.
Okay. Yeah, thank you very much. It's nice to be here. So this is very recent work, as Muit said. So it's a joint work with Shi Li, who's a last year graduate at Princeton, and I'm at EPFL in Lausanne, Switzerland. So I want to spend the first slide with convincing you why kMedian is a very important problem for Microsoft Research in Seattle. And that is, where you should locate your research centers so as to minimize the average traveling time. So my traveling time was, of course, very long to get here. So we will see some optimization on this. So to see this, we have America and Western Europe, and you can plot the concentration of researchers. We have Seattle, Silicon Valley, Chicago, East Coast, then maybe Sweden, England, Lausanne, of course, Germany, and so on. And it looks like you did your homework, because now if you plot Microsoft Research, we have Seattle, of course, where we are, Silicon Valley, New England, and now a new one in New York. But then there's a Cambridge. And obviously you should have moved this down to Lausanne to So that's all. But more seriously, so like when you want to place your Microsoft Research location, you can think of different objective functions. So in theory, we often consider minimize average distance or minimize the maximum distance. So these problems are known as kMedian or kCenter. And when I start to look at these problems, I was not really clear why we call them like that. So let me just spend one slide of motivating the name of these two problems. So let's look at the median problem, but now I formulate it a little bit differently than we're used to. So we have clients on the line. I want to put one point on this real line as to minimize the average distance. So if I just put a point here on the line, then I can see that if I push it to the left, then I will decrease the distance for these 3 clients. But on the other hand, I will increase them for these 6 clients. So it looks like a bad move to move it to the left. On the other hand, if I move it to the right, then I will decrease the distance for 6 and so on. So this is the green direction. So then I just move this point along the green direction until I find equilibrium. And this then coincides with the median as you know it. So that's why we call it median. And then for the center, we simply want to find a center. We look at the 2 extreme guys, and then we place our guy in the center. Okay. So this I want to say that this is a little bit insensitive objective function, because once I have my point here, no matter where I place the light red clients, they will not affect the objective function. Okay. So kMedian now is that we generalize the open K points, facilities, and it's not a real line, it's a metric space. And what we will use is that the distances are symmetric and the triangle inequality is satisfied. So for this case, I think it makes sense to open these 2. And for kCenter, you could open the same 2, but it also makes sense to open this outlier here, because you only care about extreme cost. Okay? So any questions on the problems?
I didn't hear that last bit.
So I mean, intuitively here, this guy is bad luck for him. So we should open 1 in each cluster. But for kCenter, it doesn't really capture that, because you only measure the maximum distance. So maybe, this is also an optimal solution as well as opening 1 here. So I'm considering kMedian, so I want to motivate, the objective function of kMedian. So the important thing is that we understand kMedian. So another point in favor of kMedian is that if we look at the state of the art of the kCenter problem, we have a very good understanding. So there's a greedy, very simple 2-approximation algorithm. And you can also make it LP-based and so on. And this is the best we can do. Okay? So we have a complete understanding of worst-case behavior if we look at kCenter. And then some people don't like worst-case behavior. So I have this image from Geneva. So this is, in the winter when it gets cold, then it gets very humid next to the lake. So if you go for dinner and you park your car next to the lake on a cold day, then when you get back, you will find it with ice covering it. And you cannot open it until it gets warmer. So that's to say that sometimes, worst case happens. So it makes sense to keep into your planning. Okay. So we know everything about kCenter. So what about kMedian? Can we do as well, or can we answer to understand what we can do for kMedian. So what do you think? You think we can do better for kMedian or kCenter, or you have no idea? Muit, you have no guess.
Well, we should do better.
Okay, yeah. So so unfortunately we don't know, but you know, but at least the hardness says that we cannot do better than 1 + 2 over e. So this is by Jane et al. In 2002. And what we don't know how to do better than 3. So there's quite a big gap. Or we didn't know how to do better than 3. And my guess would be that this is tight. So just by working on it. But this is a guess, underline, and so on. So I don't know. But it feels like we should be able to do better. But our current techniques doesn't allow us. Okay. So what we're going to talk about today is like the best approaches so far for approaching this problem. So what's the known techniques? Then I will state our results. And I find it's like 2 independent parts. And I think the first part is maybe most interesting. And that is, this K is a hard constraint. We can now open at most K facilities. So what we show is that we can turn this hard constraint into a soft one. So we are allowed to violate slightly. But then how much we violate this constraint will affect our running time. Okay. But as long as we violate it by constant, it becomes a polynomial time algorithm. And once we have this result, we can design what we call is a pseudo-approximation. Okay. And combining this gives you a better approximation. So just before I start a little bit about non-techniques, let me make some conventions. It will be convenient to distinguish the points in the metric space where we can open a facility and the client. So I will always draw the points where I can open a facility by squares and the clients by circles. And the goal is then to open K facilities. So if we would open 3 facilities, maybe we open this. And once we know which facilities to open, it's trivial to assign the clients, just to the closest facility. So what is the algorithm? Okay? So the first algorithm, if you looked at the median on the real line, we just started with any point and we greedily improved it. Okay? So let's try to do that for kMedian. Okay? So what we do is to start by opening any K facilities. And while there exists a swap that decreases the value, we do it. Okay? So swaps means that I start with these 2 guys, then I might close one of them and open another one. And I do this as long as there is one that decreases the objective value. So maybe I swap this and then I'm happy. And this actually gives you a 5 approximation algorithm. So this was proved by Arya et al. In 2001. And now if you have a swap, the next thing you would do is to look at p swap. So instead of just closing 1, you would close p and open p and so on. And this gives you a 3 + 2 over p. Okay, so and this is the best. So this, yeah, if you let p be sufficiently big, it's 3 + epsilon approximation. So this is the best that we have. So that's what we have.
I know there are examples where it doesn't have to be better than this.
Right. So this is tight analysis. Maybe you can come up with some smarter swaps, but if you just do these swaps, then it's tight.
And how long does it take to convert?
Yeah, so that depends on, I mean, it's not clear, right? So that's where this epsilon comes into play. So this is not 3 + 2 over p, but you need some slack in your inequalities. So you say that in each step, I want to improve at least this much, otherwise I stop. If there's no swap that improves this much, I will stop.
That wasn't quite the question. So if you, I mean, are there bad examples where it could take many, many steps?
Take into the p steps.
Yes. I don't know if that's the bad example, but the upper bound is n to the power of p. But I mean, yeah, that's not the main focus of their part. So anyway, but this was in 2001, and since then we have tried a lot to do better than 3. And one very promising candidate to do better than 3 is, linear programming. So
It's not even clear polynomial. Into the K.
no, that's why I said you need a slack in your improvement.
But in a typical naive local search, might not
Yeah.
be polynomial type.
Yeah. Yeah.
If K is fixed.
Then you will solve the optimal.
Yeah. Okay, so I know you don't like, probably most people don't like linear programs, but you will not need to understand the linear program in this talk. I just wrote it here. But to understand these approaches, what you need to understand is that there are variable yi, and you should think of this, that it should take value 1 if we should open that facility. And then there's a variable xij that takes value 1 if j is connected to I. Okay. So now this objective function is just the sum of average connection cost. Okay. And this is that we can open up most k facilities. Here, each client is connected. And here we say that if a client is connected to facility I, then that one has to be open. So don't worry if I went through here quickly. But now, many here like randomization. So what we do here is to interpret this yi's as the probability that the facility I is open. And then once you have this intuition, okay, then the first time you would try is to just open independently at random each facility with probability yi. So this is not that good idea. So why? First of all, we have to satisfy this constraint that we can only open k facilities. And then there is a real problem that in the neighborhood of some client, we might not open any facility. So there might not be any facility at all open close to client. Okay. So maybe that's the most serious problem. So what people have done is that they very carefully grow balls. So they take any client, and they close a ball there, and they grow this ball until the LP says that inside this ball we should open at least one facility. Then we grow another ball and so on. And they do this very carefully. Now they do the randomized rounding so as to ensure that they open at most k facilities and at least one is open in each ball. And the marginal should be satisfied. So maybe we open 3 facilities in this example. And this was the first constant approximation. So it's this careful dependent rounding gives 6.25 approximation from 99. And now, they have worked on this quite a lot. So now the best one from this year is a 3.25. And this is extremely careful dependent randomized rounding. So, and they think that it's a better than 3, but the analysis is very long and so on. Because, it's not clear how to grow these subsets and so on. So, by the way, so here we see a clear difference between a related problem of facility location. Because in facility location, this technique gives nearly tight. Whereas here we have the hard constraint that we can open k, and this makes problematic.
In facility location, what is the constraint there?
So that's the next slide. So that's good. So in facility location, same as kMedian, but no hard constraint that the most k facilities is open. Instead, we have an opening cost. Okay? So each guy can be open, but we have some opening cost. So, but there is a very nice relationship with kMedian that I now want to talk to that we will use. Okay? So this comes from simple economy. So now if we can set prices on facilities, suppose you set the price to be very cheap, then we would open many of them. If you put the price to be very expensive, then few facilities will open. Okay? So what would you do? You try to find a price and use the best known algorithm for facility location to get the solution that opens basically k facilities. Then this would be a solution to kMedian. Unfortunately, this function, is not continuous. So you cannot be sure that you open exactly k facilities. So what you do is to find prices so that if you change it slightly, you find one solution that is slightly lower than k and one slightly bigger than k. And that's the intuition by these bi-point solutions that Jane and Vatsarani introduced in a very nice paper. So what they prove is that, okay, so let me just explain here. By losing a factor of 2, we can find 2 solutions. So think of k equal to 3 here. So in one solution, I open less than k facilities, so the blue solution. In another solution, I open more than k facilities. So I open 4 facilities here in the green solution. And in each then defines a pseudo solution where I connect the client to the closest in the green and the closest in the blue. Okay, so 2 solutions. And what they prove is that we can think, by losing a factor of 2, we can assume that the LP solution is a convex combination of these 2 solutions. Okay? So I will just take the convex combination and I get a very structured LP solution. Yep.
I think that both are examples where the cost of opening k facilities is a convex function of k. Is that, people ever look at that sort of more general cost functions?
I don't know. Probably. That would be my result.
Like these sort of 2 extreme cases,
Yeah, that's true. I don't know. But so I understand here. So I have 2 solutions, and the convex combination defines a solution to the LP. So I just draw it like this. I can order them like that, and all the clients in the middle, and they will be connected in some way. So one blue solution and one green solution, and the LP will be a convex combination of the 2. And then what they show is, it's quite easy. Once you have this structure of the LP solution, you can round it. So they show that you can, losing another factor of 2, we can convert such a LP solution to a solution that opens at most k facilities. So if you lose a factor of 2 here, and you lose a factor of 2 here, so you get a 4 approximation. So this, first they lost a factor of 3, and then they lost a factor of 2. And this one is tight. because if you're given a star, here we have k plus 1 facility client pairs. So these clients, they have distance 0 to these facilities, and they have distance 1 to this topmost facility. Okay. So we have k plus 1 green. In our green solution, we have k plus 1 facilities open. The cost of this solution will be 0. Here we have 1 blue guy open, and the cost of this one would be k plus 1, because everybody would have distance 1 to him. So it's extreme difference between open 1 more facility than we allowed, then we get a solution of cost 0. But if we open k facilities, you can see that the optimum is 2. And the LP would tell you that we should open this solution with probability 1 over k, and this one with k minus 1 over k. So this is the worst case known for the LP, so that's an inequality gap of 2, if you think about it. And our algorithms will be obtained by staring at this graph long enough. And then, I mean, it's a very simple graph, but it gives you a lot of insights. Okay. So you understand this instance, we have k plus 1 facilities here. And if we take the green solution, it will have cost 0. If we take the blue one, it has cost k plus 1. So therefore, the LP has value 1 plus 1 over k. Because it says that we take the blue one with probability 1 over k, and the green one with probability k minus 1 over k. Okay. So just to summarize, the best argument is local search based 3 plus epsilon, best harness. And this goes using such as is that hard constraint that most k facilities can be opened. Okay. So for facility location, we have almost tight results. So what's our result? So as I said, we're going to stare on this graph for a while. So what we prove is that we can get a 1 plus square root of 3 plus epsilon in n to the power of 1 over epsilon. But OK, so that's an improved factor, it's 2.71. But I think the coolest result is that. So if you have an R pseudo-approximation algorithm that opens k plus c facilities, then this can be turned into a R plus epsilon approximation algorithm that opens k facilities and runs in time n to the power of c over epsilon. So this shows that, for example, this inequality gap for the LP disappears because I can just open all the green ones. And then I can apply that theorem as a black box to get a good approximation. So
Pseudo, you just mean that you're opening k plus c facilities.
yeah, you could call it bicriteria if you want. So the problem with bicriteria was it's not a multiplicative factor. So I don't, bicriteria, so many people means that you would have a multiplicative violation in the number of facilities open. And that would kill our result here, because then your running time would be n to the power of k. And then we just do a pseudo-approximation that is 1 plus square root of 3 that opens all the 1 over epsilon centers. So this is, I think it's very good. This is good, but probably you can improve this. OK, so let's prove this theorem. So let's get it. So the idea is very simple. So if you look here, you know, so here we have the clients, which is students, and then we have the universities. You know, so if the clients are not too concentrated around a university, then if we just remove one university, we will make some guys angry, but they're only few compared to the total number of students. Okay, so kMedian objective allows us to make some clients very angry. It will not affect the overall objective very much. Okay, so that's the idea. So that is the two extremes. We have a very sparse instance that no clients are too concentrated. And then we have the dense clusters, as you could see in the integrality gap instance. Okay? That we have clients that have connection cost 0 to facilities. So clearly, if we can open 4 facilities here, it has a much lower cost than if we can only open 3. So so removing a facility here will increase only if we remove one facility, then we will increase the cost by maybe a factor of 1 over k. Something like that. No, not too much concentration around this. So some guys will be unlucky, but they will be rerouted. But if we remove one here, then we will increase the cost with a huge factor. So the question is, this seems like an impossible thing to prove, that if I take a solution that opens k plus 1 centers, how can I turn it into a solution that opens k centers without increasing the cost? And the answer is that you want to remove these kind of instances. Okay? So you want to pre-process away these instances. Yeah, so removing a constant number of spheres from a sparse and then the proof will be based on that. If we can remove a facility here, then we will increase the cost by little, and we will now prove that we can concentrate on sparse instances without loss of generality. So let me take some time. So what do I mean by sparse instance? So I say that an instance is A sparse if for every facility I look at that facility here, and now I look at all the clients around it, which the radius of this ball is the distance from I to the facility open in the optimal solution. So here, I'm only allowed to open 3 facilities in the optimal solution. Maybe it's the green facilities. Now I draw a ball around this facility I that I'm considering with radius di opt over 3. So here I have di opt, and the radius here is 1/3 of this distance. Okay, and all the clients inside this ball should have a connection cost in the optimum that is most A for it to be A sparse. Does that make sense, the definition? Maybe. Oh. I look at a small ball around a facility. I look at all the clients. What's the connection cost in the optimum? I don't want it to be very big compared to opt. Because that would mean that if I remove this facility, then I would increase the cost a lot compared to opt.
So is the I opt the average connection cost of a client to I in the optimal?
No, so this di opt is the distance from the facility I to the optimum facility, to the closest facility in the optimal solution. So, but the connection cost of a client here in the optimal solution would be at least most 2/3 this.
When you say instance, this is an instance of choosing k+1 facilities, or?
Yeah. Yes. For simplicity, let's think about k+1.
And when you say every facility, you mean not every facility that's included in any solution, but just every potential.
Every potential facility yes, any potential facility location. Right. Good. So this guy is he's not sparse because we can see that the clients in this ball will actually be the whole optimum cost in the optimum solution, right? If I have these clients here, these guys will have cost 0, these cost 0 in the optimal solution, but these ones will have all the cost of the opt. So this guy is a dense instance. Of course, I don't know opt. But
so in your sparse instance, you can still allow those 3 clusters. If you just had those 3 clusters, you would still call it sparse.
Yes.
Right? Although it's
yes.
dense.
Yes.
You still call it sparse.
Yeah. So it's a little bit confusing in that way. So if the dense things are around the facilities that are opened in the optimal solution, then I still call it sparse. But because I call it sparse because the problem is that maybe the LP tells me that this guy is open with high probability. So basically the LP fools these clients, and that's a problem.
So here you're fixing one particular optimal solution.
Yes, I assume the optimal solution to be unique. So you can also do it with Joel Adams, with LPs. Okay, so how can we now obtain? So of course, not all the instances we see are sparse, but how can we assume sparsity without loss of generality? So how would you do to obtain a sparse instance? So if I know the optimum, suppose we know the optimum, what would you do? Well, the first thing would be, okay, let's remove all the locations that are not part of the optimum. That would be, then we would have a sparse instance. But that's a little bit too good to be true. So let's try with something weaker. So while there exists a dense facility, okay, what I will do is to remove this facility and any facility within that is closer to this facility than the optimum. So I remove this facility, this facility location, and I remove anyone that is closer to this one than the optimal facility, the facility in opt. So I remove that one, and I remove that one.
So are you trying to do this?
So I didn't draw the clients here.
Yeah. But
so now,
is this a thought experiment or is this an algorithm?
This is the algorithm that we will see that we can turn it. This is of course not a polynomial time algorithm because we don't know opt, but we will see that it doesn't matter. Okay. Yeah. You will not implement this algorithm, but no. This you will see that it doesn't matter that we don't know opt. That's why I said. I mean, we can always if we knew opt, it's trivial. We can remove all the locations that is not opt, but that's not good. So now I try to do something weaker that I can turn into a polynomial time algorithm. So let's look at something weaker, and the weaker thing is that I am looking for opt over t sparse instance. So if I have an opt over t dense facility I, then I identify this facility I here. And now I will remove it, because I know that I'm not using it in the opt. And I will remove any facility that is closer to this one than the optimal one, because I know they are not used in the opt. So I remove that one and that one. Now I iteratively do this. Okay? I find these balls. But now the key thing is that these balls will be disjoint by the way we constructed this iterative algorithm. So how many balls can we have? So the opt over t dense means that the connection cost of the clients in this ball was opt over t. So we can have at most t balls. Okay? Because balls are disjoint, we can have at most t balls, because otherwise opt would not be opt. Okay? But now we can guess these balls, even if we don't know opt, because we only have t ones. We can just enumerate all possibilities in n to the power of t time. So that's why it was a thought experiment, but you can easily turn it into an algorithm by paying a large polynomial factor. So that's why we can look at sparse instances. And now maybe you want to believe me, as we saw before, that if we have a sparse instance, then it's quite easy to turn it into one that only uses k facilities. There are some complications, but so now what we look at is, let's look at this guy. Let's try to remove him. Let's try to analyze how much the distance of the clients in this. So if I have a solution, it naturally partitions my space into Voronoi diagram, right? So all the clients in this one will be connected here and so on. So now let's look at what happens if I remove facility I. Well, if this client here is far away from the facility, let's say at most a factor 1 over t times li, which is the distance to the other one, then his distance will increase by at most a factor of 11. Okay? Just by the triangle inequality. But now if he's too close, well, then we know that since it was a sparse instance, these clients cannot contribute too much by removing this. And that's it. Okay? If these optimum are far away from the blue guys. So there is some, if you don't know, but there is a technicality to say that if all these guys are very close, then we are in trouble. But then the thing is that if they are close, then we basically found the optimal solution already, and we can guess the symmetric difference. But that's a technicality. Okay. So for any t, we obtain an opt over t sparse instance in time n to the power of t, run pseudo-approximation algorithm on sparse instance that we'll define later, then massage it in time n to the power of t into a solution that opens k facilities in cross. So this t then comes up in the running time. So that's why I have this c over epsilon.
Where do you see the root 3 coming up?
Sorry?
The square root of 3, where is that?
Yeah, that comes now. Yeah. So yeah, we call it a star algorithm. So this is the stars we have in Sweden for Christmas. We hang them in. It's very dark, so we have a lot of lights in the rooms. Okay. So it's not. It's not called a star algorithm because it's the best algorithm. It's called a star algorithm because we use stars. Okay. So how to run one star? Now, when we are allowed to open a little bit more facilities, how would you do? Okay. So it's kind of the LP tells us that we should open the center with probability 1 over k, and we should open the green solution with probability k minus 1 over k. So now the algorithm will simply open the center with probability A, or otherwise we would open all the leaves with probability 1 minus A, so probability B. Okay? So either open this or all the leaves. So in the worst case, in this case, we will open k plus 1 facilities. And the expected cost is the same as the LP. Okay, so there is, of course, let's think about not too many leaves. If you have many leaves, you have to be a little bit, then you cannot do it. But it's enough to think about it. Okay, so rounding several stars, how would you do?
Are you opening, or in the worst case, you open all the k plus 1?
So if you have way too many leaves, what you would do is always open a center, and then I'll open like a B fraction here.
So ideally, you want to say you could do the same thing as the previous papers, where you had these two solutions, right? Which one more and one less, and you pay basically same as the LP or twice the LP.
Yeah, so that's why I say it's not. I think one can improve it. So we start by losing a factor of 2 to get this kind of structure. But this was the integral. Yeah. So Okay, so how would you round several stars? Okay, so pick an A fraction of the stars randomly. Okay, so maybe I pick this fraction. For those guys, I open the center, and for the other ones, I open all the leaves. Now, maybe I pay, number of visits obviously k plus constant by some rounding problems. But this is assuming stars are of the same size and not too many leaves. Okay, so it gets more complicated if you have different number of leaves for every star and so on. But let's not worry about that.
And we have constantly many stars too, right?
No, we might have many stars.
Okay, so then that fraction of the stars we pick randomly has to be careful. We have to be careful.
Yeah, we do uniform at random an A fraction of the stars. That's just that I want to expect the connection cost of a client is A, and here the expected opening is A, and the expected here is B.
So that's not a typo when you say pick an A fraction.
No, I'm sorry. It's difficult to write A.
Some number.
Okay, so now the square root of 3 comes into play. So no, next slide. So okay, so how is the whole algorithm now when we saw this? Okay, so obtain point solution, losing a factor of 2, as we saw that we could do from Jane and Bazzirani. And now we should obtain stars from this instance. And the way I obtain stars is to look at each facility in green and take the cheapest edge to the blue. Okay? So each edge here has a green distance and blue distance. So if I sum these distances up, I get the distance of the whole edge. And for each green, I connect it to the blue to take the cheapest edge. So this gives me some stars plus some clients that goes in between stars. Okay, I cannot remove the clients, but I will define my stars like that.
No, it's not clear. So how do you define the stars?
So for each green guy, I pick the cheapest edge, where the cost of an edge is this green distance plus the blue distance.
So edge to where? Edge to the blue guy.
To the blue guy. So I see this as an edge with a green part and a blue part.
So how do you end up with a green guy connected to two blue guys, as in the second picture?
Yeah, because here I have many clients, right? So this guy, so these are part of the stars. These are the ones I picked, but I will have to keep the other clients. So let me redo it. So for each green guy, I will pick a representative, but I have to keep all the clients. The representative I pick is the cheapest. So I have some cost here. The cost is the length of the green part plus the length of the blue part. So now I have a unique representative for each green guy. So it will be stars based on the blue. Maybe they have different sizes and so on. But
this only involves some of the clients.
Some of the clients, exactly. And this one is one of the other ones that I didn't pick as a representative. But what's important here is now that if we look at the distance of this client to that one, what's the distance? It's this green part plus this green part plus this blue part. But since we picked the representative here to be the cheapest possible, we have that the distance here is at most the distance here. So the distance here is 2d2 plus d1. Okay. So this says that every client will be pretty close to the center of that star. And why is that good? Because remember our algorithm either open the center or all leaves. So either the leaf is open, we are very happy, the center is opened, or none of them is opened, and then we can connect them here, because we know that this guy is open if this one is not open. And now now you write down the expected connection cost, and then square, and you get that this is 1 plus square root of 3 over 2. Okay. So that's the whole thing. And the plus epsilon and so on becomes because you have to deal with different size stars. If you just have the same star sizes, you get plus 2 or plus 3. Okay, so the summary is, I think the most interesting is that we managed to turn this hard constraint into a soft constraint. So this gives a new point of view, and what is very nice is that this standard LP, we thought it was not good enough to answer what we think is right, 1 plus 2 over e. But now it might be good enough, as we can open a constant more facilities. So just by looking at this standard LP and try to round it, opening a little bit more facilities, even if I only open one more facility, I don't know of anything worse than 1 plus 2 over e. So it might be possible to use the standard LP. And then it was first obtained by studying these hierarchies for So LP here is for kMedian. And then Shi Li, so that we can do it without hierarchies, which is easier usually. But it will be interesting to see, if similar things done used with other problems with hard constraints. So in particular, this kMedian, if you have capacities on the number of clients that can be assigned to a facility, then there is no constant known. So if one could relax these, then the problem gets easier. Okay, so thank you. Yeah.
So, because in between this, kMedian, which is L1 optimization, and the other one called L infinity, of course, there are all these different LPs, and I guess L2 would be the easiest, but
there was one more practical researcher that visited Mohit this morning. Exactly, that was his question. So I don't know. So I think we are looking at this because it's easier. It's a LP. And we haven't understood this yet. So, but there are, based on the 3 approximation local search for kMedian, there is a 9 approximation for k-means.
But if you do the version with L2, is that, do you know what?
Yeah, that's k-means. That's k-means. That's k-means. So there is a 9 based on the same technique as local search. But maybe you could get a better here. We haven't looked.
One would expect that one to be easiest.
Okay. Yeah, you don't have that intuition, but maybe.
It's not clear, yeah.
L2 is easiest.
Okay.
I guess the power he's getting, I guess he has an LP to work with L1, which you don't have. And
you can solve the convex problem.
no problem as well, yes.
Yeah, so maybe that we should actually look at that. It's strange that because they seem to be more interested in k-means, the practical people.
Right, but it seems because you started with presenting those two problems,
right?
Somehow extremes, and both have some non-uniqueness, and even for the case of choosing one, even if you have points on the line, median.
Yeah, you should be able to do any LP. So. Yeah, I agree. You should be able to do any LP norm.
Morally, L2 should be easiest, so the fact that it's not means, I think, that
maybe it is easiest.
The same indication is not given to it.
Yeah.
That's sort of related to a question I had, which I was wondering if there was like a general known lower bound for LP. Right? Like, is there a form of like lower bound which says given
You mean LP as in linear?
Yeah.
No. LP as in the norm LP.
I don't know. Do you know? So I think we like these extremes because they're easy to think of in terms of LP or
Both of them are,
yeah.
So you mentioned that previously you had an algorithm based on some hierarchy.
Mm-hmm.
What was the hierarchy, and was it just for 2 of these pieces, or only like for the second part?
No, it was only for the first part
For the first.
to relax the constraint. So instead of doing the enumeration to get a sparse instance, you can just condition in Cheryl Adams. So that this is like events, is this the facility dense? And then you can condition on these events. And you have to condition on that many events. So Cheryl Adams is enough. We'd added one constraint. But
Basically, like, you will have to go to as many T hierarchies where you have the T circles that you guess.
Yeah.
So you condition on those centers not being in the
yes.
solution?
I condition on. So here we said sparsity without. So here I condition on this guy. So here I said what I do is so I condition on for if this facility is sparse is dense, then I will condition on this one being the closest opened. And this will force all these to be closed. So that's the event. Then all the LP values will be 0 for this. I can remove them.
Do you need extra variables for that, or?
No. So the only I will have to have a reinterpretation that XIJ stands for not the facility J is connected to, but it's the closest open facility, which is what you would expect.
Also, So for the star algorithm, do you, for that, do you use the fact that absolute instance is sparse?
No.
No, you don't need to.
No.
So if I just understand, like for that problem, basically you give a 1 plus square root 3 over 2 approximation.
Yeah. So this shows that they are not the toughest extreme points now, since you can open more than k.
So how does it compare to 1 plus 2 over e? What is this number set to?
No, it's better.
It's better than.
So this shows that the hardest integrality gaps are not in this form.
And is this analysis tight? 1 plus square root?
We don't know. No, it's probably not. We don't. Yeah, analysis is probably tight, like edge by edge analysis. But you can probably round this kind of. But you don't want to lose a factor of 2 to start.
Any more questions? No? So let's time the speaker again.
Thank you.